Welcome to the Semblex Solutions at Work mini video series. I am Brant Ruskowitz, the Product Development Manager at Semblex, which is a specialty fastener company in the Chicago area. In this video series, we will evaluate the latest fastening technologies available through Semblex and look at some of the potential applications for each technology. In the previous flow drill fastener basics video, the Semblex Solutions at Work video 3, we discussed traditional flow drill fasteners and some of their limitations. One of those limitations was that traditional flow drill fasteners could not flow drill through aluminum layers greater than 6 millimeters thick. In this video, we're going to discuss that limitation and how the OptiFlow low torque tip design feature can overcome it. Let's try to drive a traditional flow drill fastener into a material that is too thick. In this case, 8 millimeter thick 6061 T6 extrusion. As we can see, the fastener breaks into two pieces. In serial production, this would be a very difficult joint to rework, but let's look at why this happens. When a flow drill fastener is installed, the drive system will record the torque applied to the fastener. We can view this torque curve and break it down into the different installation steps of finding, penetration or passage, thread forming, and tightening. During the penetration step, we're forming a hole in the material, and the deeper we get into the material, the higher the torque will climb, until we've fully formed a hole. After this, we'll enter the thread forming step, which is typically where we're going to see our highest torque in the process. The peak value here is called the thread forming torque. If that thread forming torque exceeds the torsional strength of the fastener, there's a chance the fastener will break into two pieces, as we saw in the video. But why does the torque get so high? Well, let's look at the dimensions of a standard flow drill fastener. If we compare the tip diameter to the minor diameter of the thread, we can see that the tip diameter and the minor diameter are almost the same. What this means is we're going to create a hole, and then when we go to form threads into that hole, our material is already near the root of the thread. So when we go to move material during the thread forming process, that material really doesn't have anywhere to go. Some of it will flow upwards or downwards, creating downward bushing or an upward bushing that can drive a sheet gap. But it will also drive large compressive stresses that will drive up the thread forming friction, in turn driving up the thread forming torque. There are some different ways that we could go about solving this problem. We could look at global fastener properties, such as material or plating. If we change the fastener material, we could make it stronger, which would increase the torsional strength and allow us to go through thicker materials by tolerating higher torques. However, this is going to be accompanied by an increased fastener cost. We could also change to a lower friction plating. This may or may not have a cost implication, however it has another large risk. Many of our flow drill fastener users are using the same fastener in a variety of different joints. Some of those are thin, some of those are thick. A lower friction plating is going to decrease the thread forming torque, but it's also going to decrease your stripping torque. So essentially, you could end up trading torsional failure in thick materials for strip out failure in thin materials. Neither of those are good options. Since changing global fastener properties has potential negatives regardless of which path we take, Semblex chose to instead focus on changing the design of a traditional flow drill screw such that this new design would enable use in these thicker materials without sacrificing stripping torque or without adding cost to the fastener. The OptiFlow low torque design solves this issue of high torque simply by slightly increasing the tip diameter of the fastener. This causes us to flow drill a larger hole. That larger hole reduces the amount of thread friction, in turn reducing the thread forming torque. Essentially, we're giving that material more space to go when we're forming threads to avoid that overly compressive load and high friction force. This simple change can reduce the thread forming torque by as much as 40%. Let's return to that 8 millimeter thick aluminum and see how the OptiFlow low torque option fares. We can see the fastener installs each time without failure. However, the bearing surface is not fully seated. To run a material this thick, you would need a top sheet with a clearance hole to get the head to properly seat, as we're simply moving too much material. This graph shows the thread forming torque comparison for a variety of different stack-ups, comparing a traditional flow drill fastener and the OptiFlow low torque option. The bars on this graph show the average thread forming torque for each of the stack ups. There's also error bars. The top of the error bar is the average plus 3 standard deviations. If that error bar exceeds the 10.6 Newton meter minimum torsional strength, that joint should not be attempted in serial production, and we see that for the traditional thread forming fastener, that happens in the thicker materials, whereas the low torque option can do all of these stack ups without any torsional failure risk. 10.6 Newton meters is the minimum guaranteed torsional strength. What that means is that if the fasteners were to be at their smallest minor diameter and their lowest hardness, their torsional strength would be 10.6 Newton meters. That in itself is quite rare, and most of our fasteners will have a higher torsional strength than that, but within production it is possible to see that number, which is why we want to make sure we never reach 10.6. Thank you for your time and attention. If you have any questions, feel free to reach out to us at sales@semblex.com. The next video in this series is going to look at the OptiFlow high performance tip option.